Have you ever looked at two different math formulas and just assumed they have nothing to do with each other? Well, today we're going to dive into two types of algebraic formulas that look totally different but are actually just two ways of saying the exact same thing. Think of it like we're learning how to be expert translators between two mathematical languages. Okay, so here are our two languages, recursive and explicit. The recursive one on the left, that's kind of like giving someone step-by-step directions. Take a step, then another, then another. The explicit formula, though, is more like a teleporter. It just zaps you straight to your destination. They might look a little intimidating with all those letters and subscripts, but trust me, they're just two sides of the very same coin.
So how in the world do we translate between them? You might be thinking you need to memorize some brand new complicated conversion process, but nope. The secret is way, way simpler. It's all about what I call the two-ingredient strategy. We just need to find the two core ingredients that both of these formulas share. Once you find them, you can build either formula you want. Easy.
All right, so what are these two secret ingredients? It all comes down to finding the start and the difference. See, every single arithmetic sequence is built from just these two key pieces of information. So let's break down exactly what they are.
First up, we've got A1. Now, that's just a fancy math way of saying the first term. We're just going to call it the start. This is your anchor, right? It's the foundation of the whole sequence, the number where everything kicks off. Simple as that. And our second magic ingredient is D, which stands for the difference. This is the engine of the sequence. It's that constant fixed number you add over and over and over again to get to the next number in the pattern. So just remember, find the start, find the difference, and you basically hold the keys to the entire sequence. All right, theory's great, but let's actually put this stuff into practice. It is time for some translation in action. We're going to take our two ingredients and start converting these formulas back and forth. You are about to see just how straightforward this really is. Okay, let's start with a recursive formula. We're given a1 equals 8 and the rule an equals an minus 1 plus 5. First step, find the ingredients. Well, the formula just gives them to us. The start, a1, is 8, and the number being added each time is 5, so our difference, d, is 5. Now we just grab our explicit formula template and plug those numbers in, and voila, an equals 8 plus 5n minus 1. We've just translated our step-by-step directions into a direct address.
Now let's go the other way. We've got this explicit formula, an equals 12 minus 4 times n minus 1. To find our ingredients here, just look for the lonely number that's sitting all by itself. That's our start, which is 12. The difference is the number getting multiplied by the parentheses, which in this case is negative 4. So now we build the recursive formula. Remember, it always has two parts. You have to state the start, a1 equals 12, and then you give the step-by-step rule, an equals an minus 1 minus 4. And that's it. We're done. Okay, that seems pretty simple, right? But what happens when the explicit formula gets simplified? You know, like an equals 3n plus 7. The parentheses are gone. So where's our starting number, a1, hiding? Is it the 3? Is it the 7? This is where things get a little more interesting. With a simplified formula like this, finding our ingredients is just a little different. The difference is actually the easy part. It's always a number that's attached to the n. So in this case, d is 3. But the start, it's hidden. And I'll tell you right now, that 7 is not our starting number. To find the real start, we have to actually calculate the very first term by plugging in n equals 1. So a1 is just 3 times 1 plus 7, which gives us 10. Now we have our ingredients. a1 equals 10 and d equals 3. And our recursive formula is a1 equals 10 and an equals an minus 1 plus 3. So now that we know that hidden start trick, we can talk about avoiding some really common mistakes. This is the key to dodging the biggest translation traps that so many people fall into. Let's make sure you're not one of them. This right here is probably the single most common mistake people make. They look at an a sub n equals 3n plus 7 and think, well, the number by itself has to be the start. So they confidently write down a sub 1 equals 7. I mean, it feels right, it looks right, but it's wrong. And yup, that's the trap. It is so easy to fall into this one. That number 7 is definitely important, but it is not the first term of the sequence. It's actually playing a totally different role. So what's really going on? Well, that number 7 is what we call the zero term. If you remember graphing lines, it's basically the y-intercept. It's where the sequence would have started if you could have a term 0. But sequences start at term 1. The real start is what you get when n equals 1, which we already calculated is 10. The golden rule is, when in doubt, just plug in n equals 1. And here's the other big pitfall: forgetting to state the start when you write a recursive formula. Think about it. The rule an equals an minus 1 plus 3 just tells you to keep adding 3. But if I don't tell you where to start from, you're totally lost. The directions are completely useless without a starting point. So you have to always state your A1. So why do we even care about translating between these two forms? Is this just some random math class exercise? No, absolutely not. This exact concept is totally fundamental in a field that basically powers our entire modern world: computer programming. In coding, programmers face this exact same choice all the time. Recursive thinking is like writing a loop. It's code that just repeats a process over and over. It's often really logical and pretty easy to write. Explicit thinking, on the other hand, is like a direct formula. You give the computer some numbers and it calculates the answer instantly. No extra steps needed. It's all about picking the right tool for the right job. And here's why that explicit formula is so incredibly powerful in the world of coding. It runs in what programmers call constant time. All that means is that it takes the computer the exact same amount of time to find the 5th term as it does to find the 5 millionth term. Why? Because it doesn't have to do all the steps in between. That kind of efficiency is like the holy grail of writing fast, powerful code. So, we've seen how two totally different mathematical languages can get you to the exact same place. It really makes you wonder, doesn't it? What other formulas do we use in our everyday lives, like a recipe or driving directions or even a piece of advice, that are really just different sets of instructions for getting to the same result? Something to think about.